Our new chapter is going to be on chemical reactions. And basically, chemistry is reliant on the understanding of how chemical reactions work. Using chemical reactions, we can understand the chemical properties of a substance. We also can use the chemical reactions to our advantage and make new materials. But we need to understand how chemical reactions work. How do we write them? And there are several different types of chemical reactions, and we're going to learn about them today. Writing chemical reaction equations requires a specific nomenclature and knowledge of what are the actual components of these equations. A chemical reaction equation is considered to be complete when it's balanced and has the following information: the reactants, the products, and reaction conditions. Now, the last one here, the reaction conditions, may or may not be listed with your chemical reaction equation. But you need to specifically have this information here, the reactants. And reactants are basically what you react or start with before you do the chemical reaction. And the products are what results when you do the chemical reaction. What do you produce? What do you make? Or what do you end with? This information may be required if your chemical reaction is a specific type that requires other additional features, such as high temperature in order to work, low temperature in order for it to be made so it's safe. If you're doing some type of cross-linking reaction, you may be needing a UV light, and so it'll tell you what the wavelength is for that. If you need a catalyst, sometimes it'll list that. This is not necessarily required, but balanced reactants and products are required for a complete chemical reaction. The format of a chemical reaction equation is very specific. Reactants are going to always be to the left side of our reaction arrow. Products are always going to be to the right side of this arrow. And you can think of it this way: the reactants will point to the products in the direction of the arrow. So the arrow says we're going in this direction, and we're starting from reactants and going to products. The arrow is read as yields. So if you were to read this out loud, you would say reactant 1 plus reactant 2 plus reactant 3 if there's one, yields product 1, product 2, product 3. Or reactant 1 reacts with reactant 2 to yield product 1 and product 2. Chemical reactions are complete sentences and are treated as such when you're looking up for as an English syntax, right? So, this is the way you would write it. Reactant 1 plus reactant 2 yields product 1, product 2, period. There are three ways to write a chemical reaction equation. Now, for us, we're going to only use one way to accurately represent the chemical reaction equation. However, you have to be aware that there are other ways to write these, and you may see these at some point during your lifetime, not only in chemistry but elsewhere, when you're reading stuff in print or looking at other journal articles or other means of communication. So the first and most basic way of writing a chemical reaction equation is using just words. When we write it with everyday words, and we don't use any chemical formulas. The only basic information that is transmitted to the reader are information about the reactants and products. And here's some examples. So let's again look at this as our model chemical reaction equation that is fully developed. But let's say how we can translate it into words. So we know this compound is a reactant, and this compound's reactant. So we'd say lead 2 nitrate reacts with potassium iodide and yields lead 2 iodide and potassium nitrate. So there we go. Here's my yields and my two products. It doesn't say anything about this aqueous thing, this solid thing, the ratio of the reactant A to reactant B, or the ratio of product A to reactant A. Doesn't say anything like that. It just tells you the basic information of what's going on in their chemical reaction. And sometimes you may see it written in a little bit differently. You might see that the products are listed before the reactants. And this would emphasize something in print, that these are more concerning than the reactants. For example, if they want to highlight or bring your attention to some dangerous chemicals for some reason, whatever reason, they could put that first, like potassium nitrate and lead iodide form when we mix these other two things together, lead nitrate and reacted with potassium iodide. So you're looking for keywords like form, to determine whether or not the products are listed first or the reactants are listed first. And in this case, it's very easy because it says potassium nitrate and lead iodide form when lead nitrate is reacted with. So these are my reactants, and obviously these are my products. The skeleton equation uses chemical formulas but is not balanced, and we'll talk about that a little bit later. And so you don't know how much of each you need to add, but you do know what the chemical formulas are, so you do have an understanding of what the materials are. And it's written more in scientific language than it is in word language, right? I'm not a big fan of the skeleton equation. I'd rather see it written in words, or this, or the complete way. But this does tell me the information I need, and I can then quickly go from here to arrive at the final type, which is our complete and balanced equation. And that, as students, you will be doing from now on. You will not be doing this, because this is our most complete and most accurate way of doing this. So the balanced equation gives me the correct molar ratios. In other words, how many molecules of this I need to react with the number of molecules of this to give me these. It also tells me the phases of each type of starting material and starting material or reactant and products. So it's telling me that in this case, I'm dissolved this material in water. This material is dissolved in water. This material is a solid, so that means it's probably precipitated out. And this material is dissolved in water. So I know everything I need to know here. I know the materials. I know the ratio. I need 1 molecule of this for 2 molecules of this. And I make 1 molecule of this and 2 molecules of this. And I know what form they are in, aqueous or a solid. So as part of your homework, what you're going to do now is stop the video, copy these things down, and then you're going to underline the materials that are the reactants and circle the materials that are the products in each one of these situations. So underline the reactants, circle the products. Bring that written information down to you when you come back at school start on Monday as evidence that you completed the assignment. All right, so stop the video now, complete that, and when you're ready, start the video for the next part. So of the hundreds of thousands of chemical reactions that go every day in our lives, they can all be listed or broken down into 5 basic types: single replacement, double replacement, synthesis or combination, decomposition, or combustion. Some folks list a 6th type called acid-base, but an acid-base reaction type is a very specific one, and if you look at it from a higher level, it can be fit into one of these 5 types also. But because it's an acid-base, they sometimes give it its own category. We are only concerned with the 5 ones that are listed here: single replacement, double replacement, synthesis, decomposition, and combustion, which is what we're going to learn about in the next few minutes. So probably the most simplest form of chemical reaction is the single replacement type. This is when one atom replaces another in a compound. The analogous would be this. Suppose you go to a dance with a date, and that's you right here. And then after you arrive, your date spots somebody that she wants to dance with, or he wants to dance with, right? So now that new person arriving comes over and dances with your date that you arrived with and forms a new couple. And then you're left out in the cold here. So you're dateless and not dancing, right? That would be one type. The other type is that suppose you arrive with your date, and then you see somebody else that you rather dance with, right? So you ditch your date, and you latch on to this new person that you want to dance with, and there's your new dance partner with you, and then your date that you came with is now single, right? So it can happen in one or two ways. One is when the metal atom replaces another metal atom in a compound, or when a nonmetal atom replaces a nonmetal atom in a compound. But the metal atom is still the same. So in this case, the nonmetal atom or atoms are the same. It's just the metal atoms are different. And in this case, the metal atom is the same, but the nonmetal portion is different. Right? So let's see how this works in real life with some real life examples. So here are two examples of the two scenarios I just talked about in the previous slide. In the first one, the cation, one cation is going to replace another cation, and then the anion is the same in both compounds. In the second one, the anions are going to switch, and the cation is the same in both compounds. So let's see how that works. So the first one, we have this compound here, silver nitrate. But now what happens is the copper comes in and forms this new compound, copper nitrate, which is right here, and the silver atom now is free. And in the second case, the second situation is that the oxygen atom now combines with the selenium to make selenium oxide, so these two combined, and my chlorine atom, which was once back to the thing, is now free, the free thing over here, right? So in this case, if you look at it, the selenium atom, the selenium here is the same as it is here. That hasn't changed. And the oxygen and the chlorine are different. In this case, the nitrate is the same in both compounds, but the copper and the silver are different. So in this case, the metal's being changed. In this case, the anion's being changed. So an extension of the single replacement reaction is the double replacement reaction type. And it's basically the same thing, except now you're going to switch two atoms in two different compounds. So it's very analogous to going to a dance. You bring a date to the dance, and your friend brings a date to the dance. And you decide that sometime during the dance, you and your friend are going to switch partners. So now your date is dancing with your friend, and your friend's date is dancing with you. So that's what it is. So you come with your partner, they come with their partner, and at some point during the dance, you switch partners. So now their partner is now your new partner, and your old partner is their new partner. All right, so that's all that happens. So it's just a switching around of partners, right? So in the case of cations and anions, you would have the cation from compound 1 get together with the anion from compound 2 as a product, and the cation of compound 2 get together with the anion from compound 1 as a product. Okay, so now let's look at some examples of a double replacement chemical reaction. So it's very simple. Let's just look at it this way. You know, when you look at this, what's going to happen is the lead here is going to get together with the iodine here. And then the nitrate here is going to get together with the potassium here. So those two are going to link up. All right, so it's basically cation from this side, this molecule here is going to get together with the anion from this molecule here. So that's what I've drawn here. The lead is now going to get together with the I, and the nitrate is going to get together with the potassium. And so when you list it over on the other side, you've got potassium iodide and then lead nitrate. Right? And then you could do the same thing down here. You got the sodium here getting together with the hydroxide, and then the bromine is getting together with the calcium, and so you get calcium bromide, and sodium hydroxide. And then the last one, you can just follow the bouncing ball. Rubidium is going to get together with the fluorine, and then the nitrate is going to get together with the beryllium, and of course then you get this, and finally you get this. So you can kind of see the pattern here. The back end of this compound is going to get together with the front end of this compound. The front end of this compound is going to get together with the back end of this compound in general. And that's how it works, right? So nothing more complicated than that, right? But you're going to see that each one of these is going to double swap. So the next type is the synthesis or combination reaction. This is basically just what it means. It's when two or more materials react and combine to form a single, the key word here is single product, one thing. And therefore, that's how you recognize it. There's only one product. So there's only one thing on the right-hand side of the arrow or in the products. So you can have many things over here. I've only shown two, but when A plus Y gives me AY, there's only one product. So here's some examples down here of what it is. You've got phosphorus reacting with oxygen to give me P2O3, and you've got pentene reacting with iron to give me this compound here, right? So you can see here there's only one product. I know it says two here, but that's something different. There's only one chemical compound over here. One chemical compound over here. So that would be your example of a combination or synthesis reaction. And people use this words interchangeably. Some people say synthesis, some people say combination. So if you see either or, it means the same thing. And directly opposite of that is the decomposition reaction. This is when a single compound breaks down into two or more products. You recognize this by having only one reactant. So only one thing over here is being decomposed. And usually the way this works is this material here is heated up to get it to decompose, right? And then it forms two or more things over here. So one reactant gives me multiple products. So here we go. We have nitrous oxide, or nitrogen trioxide, gives me oxygen and nitrogen. Calcium carbonate gives me calcium oxide and CO2, right? One compound, two different compounds. So that's how you would recognize that. So the key thing is here is one reactant, right? It has to have only one reactant. If you have more than one reactant, it's not a decomposition reaction. The combustion reaction is defined as when a compound, generally a hydrocarbon, reacts with oxygen to produce CO2 and water. We recognize it by having oxygen as a reactant and only CO2 and water as products. They are the only products, CO2 and water. So let's look at a couple of examples real quick. In this case, we have our hydrocarbon, which is again, molecule that contains only carbon and hydrogen, reacting with oxygen to give us CO2 and water. Now, this equation here is exactly what your car engine does, right, when it burns gasoline, right? You put in a hydrocarbon, octane or hexane, which is basically what most gasoline is. You put it and burn it in the presence of oxygen, and you're supposed to make only CO2 and water. So all the steam that comes out of your tailpipe is water steam, so you're doing that. And CO2, the problem is we also make some other byproducts which are not wanted, so the combustion reaction is quite inefficient in our car engines. And in the other case here, we got C5H9O. Again, one of our reactants is oxygen, and we form CO2 and water only, right? If you see on this side CO2 and water and something else, it's either an incomplete combustion reaction or it's a it's some other type of reaction besides combustion. So you've got to only see these two chemicals, CO2 and water. If you see those two, double check that you see oxygen on the reactant side. If you do, you can assume that it's a combustion reaction. Okay, we've come to the end of the tutorial video, and now you're going to do some practice on this. So I'm going to have a worksheet for you when we come into class on Monday to further enhance this, but I want you to do these problems now on a piece of paper and then bring them in as evidence that you watched the video, right? So you're going to copy the equations down on the left-hand side, and then you're going to write in this spot here whatever the reaction type is. So I'm just going to make something up. I don't know if this is true or not. Single replacement, you could write SR. And if you had double replacement, you could do DR. Combustion, you would write CMB or something, whatever, to do that. And then bring those in so you have evidence that you watched the video and did the homework. All right. So that's the end of the video. You can stop it now, finish these, and then bring them into class.